Welcome to Python mmap, doing file I/O with memory mapping. My name is Christopher, and I will be your guide. This course is about the mmap library, a wrapper to a fairly low-level operating system call that maps the contents of a file into memory. In this course, you will learn about how to map a file on disk into a memory block and why you might want to do that, reading and writing to and from said memory block, and how to use this same library for sharing memory between processes. A quick note on versions. All code demonstrated here was tested with Python 3.10 on Mac OS. If you've taken one of my courses before, you'll note I don't usually bother telling you about the operating system. In this case, the mmap library has some operating system specific variations, so my OS is a bit more important. Don't worry, you'll be able to follow along either way. I mostly stick to the stuff that is common to all operating systems, and will point out the differences between Unix-like worlds and Windows worlds when they're important. mmap has been around for a long time and pretty much mimics the underlying call in C that it is based upon, so that whole Python 3.10 thing isn't too important. I do use f-strings in some demo code, but otherwise this could go back to the dawn of Python time. mmap is based on a very low-level call to your operating system, which maps directly to a call in a C library for system memory management. Its purpose is to map the contents of a file on disk into a block of memory, so that anything you do to that block of memory is reflected in the file. That's an oversimplification. There are multiple modes of doing work, but the primary purpose typically is write to the block of memory, have it reflected in the file. Why would you do this? In the Python world, usually when you're mucking about with a file, you're loading into some sort of Python object representation. This is typically either a string, a byte buffer, or something similar. Direct memory mapping is a lot closer to the underlying file. There's no intermediate representation. This often means you can get a performance boost. It usually means less memory, because the Python object requires multiple copies of things going into memory. For example, the file might get buffered when it is read before being put into the Python object. And in most cases, you may also get a speed improvement. Since this is tied so close to an OS call, the performance boost in memory usage and speed is tied directly to the OS. That means the boost you get may be different than the boost I get, or worse, might be different between subsequent calls due to things like caching. In addition to all of this, the mmap library can also be used to share memory between processes. Next up, I'll give a bit of background into the inner workings of your computer and how that affects memory and file I/O. If CPUs, memory, and files are your bread and butter, feel free to skip this one. In the previous lesson, I gave an overview of the course. In this lesson, I'll cover background on memory and file I/O in your computer and all the stuff you'll be glad your operating system abstracts away for you. First off, let's talk about performance. Your computer can be broken down into four basic concepts: the CPU, where the computation takes place; the memory, which acts like a kind of chalkboard that temporarily holds things that are too big to fit in the CPU at a time; a storage unit, like a disk drive; and, not pictured here, an interface to peripherals like your video card. There are huge performance differences between each of these areas. I know I exaggerated the huge in that last sentence, but it truly is kind of mind-blowing. See that dot? That dot represents a nanosecond. That's 1/1000th of a second. To try and imagine that, light travels a whole 30 centimeters, or just about a foot, in that amount of time. Your CPU is so fast that a middling Intel i7 from a few years ago could comfortably do 100 instructions in that time. Now, instructions in a CPU are basic building blocks, so that's not 100 lines of code, more like 100 multiplications, but that's still a lot. Your CPU has little tiny memory things inside of it called registers. This is where it stores stuff it is operating on. But there aren't a lot of registers in most CPUs, and so there is a constant shuffle to memory to get stuff to fill the registers. Just accessing a spot in memory takes about 100 nanoseconds. The dot above is a single pixel. This line is 100 pixels long. You see what I'm doing? Instead of just accessing memory, let's read a bunch of it. Grabbing a megabyte of data takes about 3,000 nanoseconds. That's 3,000 pixels of lines there. This is something every programmer should have a basic understanding about. Going out to memory is significantly more expensive than doing something directly on the processor, and you ain't seen nothing yet. Let's take 1,000 nanoseconds, that's a bunch of those red lines, and compress them down into that tiny yellow dot. I'm back to a single pixel. You thought going out to memory was slow? Well, going to disk is much worse. Yep, you read that right. 825,000 nanoseconds to read that same megabyte block from disk. That's a 3 order of magnitude difference. It isn't relevant to this course, but there is worse. The network is even worse. Locality in computing is tied to huge performance gains. If you can keep everything in memory, it can make a big difference. If you can keep everything on the CPU, even better. All these numbers are just rough. Because of these differences, your hardware will have caches between these boundaries to help improve performance. That makes measuring things a bit weird. You'll get different results between the first and second time of doing anything. That's those caches. The difference is so stark that most CPUs have multiple levels of caches on them to help avoid going out to memory too frequently. Consider the relatively simple case of adding variables together. Variables in your program are stored in memory. The act of addition is done on the CPU. To do the addition, the variables have to be read from memory, put into registers on the CPU. Then the CPU does the addition, typically putting the result in a third register, although some hardware uses 2 registers and overwrites one of them. Then, to put the result in a third variable, it has to be written back out to memory. Think back to the latency values from before. Let's simplify this and say that the 2 variables can be read in a single access. An access costs 100 nanoseconds. In 1 nanosecond, the CPU can do 100 instructions. That means the CPU could do over 10,000 additions in the time it takes to just fetch the variables from memory into the registers. I'm sure you can guess where this is going. A molasses-like pace of disk reading is in your future. All right, let's change it up a bit and talk about different kinds of memory. Up until now, I've been talking about the physical memory in your hardware, most likely RAM. There's only so much RAM on your machine, and every process running wants some of it, so your operating system abstracts this away as virtual memory. When a program wants memory, it is given virtual memory, which could currently be in RAM or on the disk. The OS swaps the contents in and out of RAM from a swap file. This enables all the programs on your machine to use more memory than physically available. The OS simply puts some of it down to the disk when RAM is tight. If your OS is smart, it typically makes this decision based on something not being used right now. This is why computers seem to go from zipping along quickly to chugging at a horrible pace. When 2 or more processes are fighting for most of the RAM, the OS has to frequently swap the memory in and out of the disk. As disks are 3 orders of magnitude slower than memory, it shouldn't be a wonder that you notice some performance difference. Thankfully, all of this is done by the OS, and you don't have to manage it yourself. Being aware of the consequences of asking for a lot of memory can make you a better programmer, or at least a programmer whose users are less cranky about the sluggishness of their machine. Another memory concept is shared memory. The simplest model is for each program that you run to be contained inside of a process. Each process is managed by the OS and, among other things, is allocated some memory. For safety reasons, this is self-contained. You wouldn't want my process writing all over your process's memory. That'd be bad. Your program can actually have multiple processes. There are a variety of reasons for doing this, but most of them have to do with trying to do more than one thing at a time. Since memory is allocated to a process, you need a special situation to share memory between 2 processes. This is another feature offered by your operating system, and it is called, logically enough, a shared memory block. Okay, you're an expert on memory now. How about that storage stuff? Consider this bit of code which reads all the contents of a file and puts it in a variable named text, which of course lives in memory. To read the file, you have to give up control of your program to the OS by making a system call. Then the OS interacts with the disk, and it buffers the data from the disk before putting it into memory. This is a vast oversimplification. In fact, that code there is going to break down into at least two system calls, one for opening the file, the other for reading. But even that reading is more complicated. There are file pointers that need to move, there are buffers that need filling. In fact, how many system calls there will be partially dependent on the size of the file being read. And I know this seems like it might be an obvious observation, but changing the variable named text will do nothing to the file. If you want to change the file, you have to do that whole process again, but writing things down to disk instead of reading. Why am I making obvious statements? Well, mmap does things differently. And you'll learn all about that in the next lesson. In the previous lesson, I explained the vast difference in speed between the various parts of your computer, gave an overview on different kinds of memory, and briefly touched on file I/O. In this lesson, I'll show you how all those things come together when you use the mmap module to map file contents into memory blocks. If you were to write a function that did edits to a file, that function would likely read the file into a Python object, a string, a byte array, or something similar, make changes to the object, then serialize that object back onto the disk. It might be into the same file, overwriting its contents. It might be to a new file or to a temp file that then gets renamed, but the results would be similar, new bytes on disk. Instead, the mmap module provides an alternative way. It reads the file into a block of memory, which is abstracted by an mmap object, then operates directly on that object, meaning both the memory representation and the disk representation change. This is both kind of simpler and kind of more complicated. You've got less steps happening, so you might get a performance gain, but you're a little more restricted on what kinds of things you can do. Let's go play with mmap in the REPL, and I'll show you what I mean. In the top window here, I have a simple function that reads a file and reports how many characters were read. All of this is being done inside of a context manager, that's the with statement, so that the file automatically will be closed upon exiting the context block. Now, into the REPL in the bottom window. I've put a file name into a variable. This Quixote file is a text file containing 10 copies of The History of Don Quixote, pulled off of Project Gutenberg. All told, it's 24 megabytes of data uncompressed. It's 10 copies because I wanted something a bit larger than a single copy. Now I'll import the function in the top window and call it. So far so good, 23 million characters. Now, let's look at the mmap equivalent. New function up top. The first thing you'll probably notice is there are two context managers here. Like before, the file to be read is opened. That's line 5. The new bit is where the file handle from the open file is used in a call to create an mmap object from the mmap module. Like files, this object has to be closed. So like files, it gets put in a context manager to make sure everything is cleaned up automatically. Mmap doesn't use a file handle, it uses a file number, which you can get from the file handle itself. In addition to the file number, it also takes a size and an access flag. Giving a length of 0, like I did here, you will get back a block of memory the same size as the file being mapped. The access flag is similar to the mode indicator in opening a file. I'll go into much more detail about this flag later. Inside of the mmap context block, I'm doing pretty much the same thing as I did in the file read function. I'm reading the whole thing into a variable, then figuring out how long it is. All right, let's do this. Imported it in. and called it. Pretty similar. You'll notice the amount of data looks different. mmap objects represent bytes, not strings. Python strings are in Unicode, and that means they may take up more than a single byte for a character. That's why the size is different. One of the key reasons for using mmap over vanilla file operations is performance, but there's a big asterisk beside that special offer. Let's time the two functions and see the difference. I'm going to import the timeit library to do the timings. And now I'll time the file read function. Using timeit, the function got run 3 times, returning the results in the list printed at the bottom here. Pretty consistent, 0.067 seconds twice and slightly faster the third time. Let's do it again with mmap. That's all over the shop, isn't it? The first time is far worse than the vanilla code, but the second and third are significant improvements. This is where it gets messy. There are a bunch of variables impacting the outcome. First, you'll get different performance based on file size. Second, you'll get different performance on different hardware due to what kinds of caches you have. Third is how your OS has implemented the mmap call. Depressingly for me, there is a known issue in the Mac OS mmap call that makes it significantly slower than running Linux on the same hardware. A colleague of mine running the same code on Windows was consistently getting 10 times improvement. Do note that what I'm doing here is just using mmap to read some data and stuff it into a Python object. Although this might get you a performance boost, it is still stuffing things into a Python object. Depending on what you're doing, you may be able to stay inside of the mapped block, and that is where you'll see better gains. More on that later as well. In that little demo, I yada-yada'd the whole characters and bytes thing. Let's dig into it a bit more. The mmap call uses a byte array representation. That means it sees everything as the bytes that make up the block, regardless of what the data represents. In the case of a Unicode string, a single character may be more than a single byte. That means you have to be careful how you read or write your data. The boundaries between characters might not be what you expect. If you're dealing with text data that is pure ASCII, you can get away with a 1-character, 1-byte assumption, but otherwise need to be careful. If you'd asked me before running the previous code, I would have sworn the Don Quixote file was pure ASCII. But the character count didn't match the byte count, so there's something in there outside of the ASCII range. Over 70 kilobytes of something in this case. Let's go back into the REPL and see how this can mess you up. I have 3 functions for you to compare. The first one reads the file as text and prints out some data. Let me just import it and run it. Okay, I ran it on monty.txt, which has 39 characters of content. The first character is N, the 6th character is Y, and the whole string is nobody expects the Spanish Inquisition. Watch out, I hear they tickle. Now for function number 2. This one's similar to the text case, but this time I'm reading the file as binary. Importing it. Running the new function on the same monty.txt file. Okay, 39 bytes, just like the 39 characters. That'd be that ASCII thing. First byte is for E, which is the hex code for capital N, and the 6th byte is hex 79, which I then conveniently show as a character, and which is still the letter Y. And finally printing it out, you get a string representation of the bytes. Because this is a chunk of binary rather than a string, Python prints it using the byte notation, a quoted value with a B prefix. And you can see the new line at the end of it. That pesky new line? Yeah, it was there before, but in the string version, it caused the gap between the output and the next REPL prompt. subtle. You could easily miss that. Let's try these two functions with some different data. I have another file that I'm going to load. Looking at snake.txt as a string, this time the length is 26. Remember, that's in characters. The first character is a cute little snake. The sixth is an E, and the whole thing is filled with emoji goodness. Before showing you the binary, I want to show you some info about the file. This rather lengthy bit of code creates a path object, calls the stat method on that path object, and then gets the size value out of the resulting object. The 39 here is how many bytes the file is. Monty.txt had 39 characters and was 39 bytes. Now let's try the snake file. It says 35 bytes, but text pieces said it was 26 characters. That's important. The emoji in the file take up more than 1 byte each, making the total different. Let's try using the byte reading function on snake.txt. There are 35 bytes, which maps what the path object said. The first byte is F0. What's an F0? Well, the first character is the Python emoji, which takes up 4 bytes. The F0 is just the first of those 4. The sixth byte is an ASCII character, though, so you can see the M. The string representation of this gets quite messy because the bytes are printed as, well, bytes instead of the ASCII equivalents. The hex F0, hex 9F, hex 90, and hex 8D all get combined to make the snake character. All right, on to our third function. This is a course on mmap after all. The new function up top here accomplishes the same thing as the binary reader, but it uses mmap instead. I'll import it and run it. And you see the same kind of result as the binary reader. To recap, when you're using mmap, you're in byte land. Everything you do is operating on a giant byte array. If the data you're playing with is a Unicode string, you need to be careful. There are even more Monty Python quotes coming your way. Next up, I'll dive deeper into the mmap call and show you many of the operations you can do on your mapped block.